Characteristics of in-phase and out-of-phase modes of vibration. Characteristic of in-phase and out-of-phase mode of vibration. Okay. Two oscillating identical coupled simple pendulum has we know two normal modes of vibration. First is in phase mode. First is in phase mode. In phase mode. Phase mode. And second is out of phase mode. Out of phase mode. Out of phase mode. Okay. Each having its own characteristics. First point, characteristics of in phase mode. Characteristics of in phase mode. In phase mode. Characteristics of in phase mode. Okay. First, the in phase mode can be excited by displacing the bobs of the two pendulums to same side by the same amount and then letting them oscillate purely on their own. Okay. Okay. On their own. Okay. Then the in phase mode can be excited by displacing the in phase mode. The in phase mode can be excited by displacing the bobs of the two pendulums to the same side by the same side by the same amount and then letting them oscillates purely. Oscillates purely, okay? On their own. Second point. The equation of in phase mode is equation double differentiate of x plus omega naught square x equal to 0 and describe the oscillating behavior of the system when it describes the oscillatory behavior of the system when y equal to x minus y equal to 0 or x equal to y. Okay. Third point. The displacement of both the bobs or masses is the same in magnitude as well as in direction, and both the masses continuously oscillate in the same phase. Okay. The displacement of both the bobs, the displacement of both the bobs or masses is the same, or masses is the same in magnitude as well, in magnitude as well as in direction, and both the masses continuously oscillate in the same phase. It means that both the pendulums pass through their mean position or their either. It means that both the pendulum pass through their mean position or through either of the extreme position simultaneously. Okay. The displacement of both the balls or masses is the same in magnitude as well as in the direction, and both the masses continuously oscillate in the same phase. It means both the pendulum pass through their mean position or through either of the extreme positions simultaneously. Fourth point. The amplitude of the two simple pendulums is the same as A. The amplitude of the two simple pendulum is the same is that A. Fifth point. The shape or configuration of the mode is the shape or configuration of the mode is x upon y equal to plus 1. The shape or configuration of the mode is x upon y equal to plus 1. Sixth point. Each pendulum executes simple harmonic oscillation. Each pendulum executes a simple harmonic oscillation at a frequency omega naught equal to under root G by L, which is the natural frequency of free oscillations of either pendulum in isolation, okay? Each pendulum executes a simple harmonic oscillator at frequency omega naught equal to under root upon G by L, which is the natural frequency of free oscillations of either pendulum in isolation. Okay. 7 point. Point 7. In phase mode, there is no effect of the stiffness terms. There is no effect. There is no effect of the stiffness term. Effect of the stiffness term. Stiffness term is of the coupling and the motion. Is of the coupling and the motion coupling and the motion of the two masses, because of the two masses because the spring always has its natural length. It is neither stretched or nor okay compressed. Okay. In phase mode, there is no effect of the stiffness term as of the coupling and the motion of the two masses, because the spring always has its natural length. It is neither stretched nor compressed. Okay. 8 point. Point 8. 8 point. Point 8. A solution of equation first gives capital X equal to x naught cos omega naught t minus phi if the maximum value of x and y be a. If the maximum value of x and y be a, then x not equal to 2a is the normal mode amplitude. Normal mode amplitude. Okay. In phase mode, characteristics of phase and out of phase mode of vibration. Okay. There are two types of vibration of mode. First is in phase mode and second is out of phase mode. Then characteristics of in phase mode. First, the in phase mode can be excited by displacing the box of the two pendulum to the same side by the same amount and then oscillates purely on their own. Okay. Second equation, x double differentiate of x plus omega naught square x equal to 0. It describes the oscillatory behavior of the system when y equal to x minus y equal to 0 and x equal to y. Third point, the displacement of both the box or masses is the same in magnitude as well as in direction, and both the masses continuously oscillate in the same phase, it means that both the pendulum pass through their mean position or through either of the extreme positions simultaneously. The amplitude of the two simple pendulum is the same, is that A. The shape or configuration of the mode is x upon y equal to plus 1. Each pendulum executes simple harmonic oscillator of frequency omega naught equal to under root g by L, which is the natural frequency of the free oscillations of either pendulum in isolation. In the in-phase mode, there is no effect of the stiffness terms as of the coupling and the motion of the two masses, because the spring always has its natural length. It is neither straight nor compressed. X equal to x naught cos omega naught t minus pi. If the maximum value of x and y be a, then x not equal to 2a is the normal mode amplitude. Okay. Next, second characteristics of out of phase mode. Characteristics of out of phase mode. Okay. Characteristics of out of phase mode. Okay. So B. Characteristics of out of phase mode. Okay. Characteristics of out of phase mode. Okay. The first point. Okay. The out of phase mode can be excited by the out of phase mode. The out of phase mode can be excited by out of phase mode can be excited by displacing the bobs of the two pendulums, displacing the bobs of the two pendulum bobs of the two pendulum in opposite direction by the same amount and then let them oscillate freely on their own. Okay. The out of phase mode can be excited by displacing the bobs of the two pendulum in opposite direction by the same amount and then let them oscillate freely on their own. Second position. The equation of the out of phase mode is double differentiate of y plus omega naught square plus 2s by m into y equal to 0. It describes the oscillatory behavior of the system when x equal to x plus y equal to 0 or x equal to minus y. Okay, this is the equation number second. Okay, third point. The displacement of either mass of either mass bob is equal in magnitude but opposite in direction to the other mass and two masses and the two masses and the two masses continuously oscillate continuously continuously oscillate oscillate continuously oscillate continuously oscillate out of phase by out of phase by continuously oscillate out of phase by an angle of 180 degree phase by an angle of 180 degree or pi radians are with respect to each other are with respect to each other, okay. It means that both it means that both the pendulum pass through the pendulum pass through their mean position in opposite direction are in opposite directions are at their opposite extreme position simultaneously, okay. Third point, the displacement of either mass box is equal in magnitude but opposite in direction to the other mass, and the two masses continuously oscillate out of phase by an angle of 180 or pi radians with respect to each other. It means that both the pendulum pass through their mean position in opposite direction are their extreme position simultaneously in opposite direction, okay. Fourth point. The amplitude of two simple pendulum is the same. The amplitude of the two simple pendulum is the same. Is that A, okay. Fifth point, the shape or configuration of the mode is the shape or configuration of the mode is x upon y equal to -1. 6 point. Each pendulum executes simple harmonic oscillator SHO, simple harmonic oscillations at a frequency omega dash equal to under root G by L plus 2S by M equal to under root of omega naught square plus 2S by M. 2s by m. Okay. 7 point. Okay. Which is higher than the natural frequency? Which is higher than the natural frequency. Natural frequency. It is higher than the natural frequency. Higher than the natural frequency of the free oscillations okay, of the free oscillations of either pendulum, oscillations of either pendulum, okay, either pendulum, okay. 7 point, 1 minute, 7.7. In the out of phase mode, in the out of phase mode, the coupling terms as phase mode, the coupling in the out of phase mode, the coupling term S dominates the motion of the two masses, dominate the motion of the two masses, and raise the frequency of oscillation. It is because the coupling. It is because the coupling spring is either in the stretch. Coupling spring is either in the stretched or in the compressed state, okay. Only once in one time period of oscillations, period of oscillation, the spring acquires its normal length. When the masses pass through their mean position, okay. 8 point. Our solution of equation second is given by y equal to y naught cos omega dash t minus phi dash. If the maximum value of x and y be a, if the maximum value of x and y be a, then y not equal to 2a is the normal mode amplitude. Is the normal mode amplitude. Okay? Normal mode amplitude. Note. X naught and Y naught. X naught and Y naught are purely mathematical. Are purely mathematical. Are purely mathematical quantities. Mathematical quantities and do not represent the amplitude of the oscillation of either pendulum which has a value a equal to x naught by 2 for the in phase mode and a equal to y naught by 2 for the out of phase mode. Okay.